Hi, this is Jonas from VHDLwhiz.com. In this video, we are going to learn how to create a finite-state machine in VHDL. We learned how to create a clocked process back in tutorial number 17, and in the previous tutorial, we worked on a timer module which used clocked logic. In clocked logic, or sequential logic as it's sometimes called, everything happens in time steps. Everything happens in sync with the clock signal on the rising edge of the clock. This makes it a bit easier for us to develop complex logic. But what if we wanted to implement some sort of algorithm in VHDL? How should we go about to translate it into VHDL code that can work in real life? Consider this example of an intersection controlled by traffic lights. The state of the lights determines who gets the right of way and who must stop. The traffic lights transition from one state to another after a fixed time interval. Some states have longer durations than others. For example, is the green light held longer than the state where it's red in both directions. The lights may have different states, but eventually the pattern will repeat itself. There's a finite number of states that a light could be in. Because of that, the behavior of the traffic lights can be expressed by using a finite-state machine. I've constructed a flow chart of how I perceive that this intersection works, and I've given the different states appropriate names. Initially, the lights are red in both directions. We'll name this state North Next, because the lights are about to give right of way to the north-south direction. The lights in the north-south direction don't change directly from red to green. At least that's not how they work where I live, in Norway. They first change to red and yellow simultaneously for a short period of time. We'll name this state Start North. After that, the north-south direction gets the green light, while the others have to wait. We'll name this state North. Then the lights in the north-south direction will change to yellow. Of course, nobody ever runs a yellow light, at least not in this town. We'll name this state Stop North. And now, for a short period of time, the lights are red in all directions. This is the same behavior as in the North Next state, remember? I didn't name that state All Red or something like that. We can't use the same name for those states because although the output is the same, the next transition is to a different state. The next state will be red and yellow in the west-east direction, while the light is red in the north-south direction. We'll name this state Start West. Now it's time for the west-east direction to have the green light. We'll name this state West. After green, the west-east light will change to yellow. We'll name this state Stop West. And that was the last state, because after that we are back to the North Next state. The pattern repeats itself. Do you see why it's called a finite-state machine? There's a finite number of states in this chart, 8 different states to be exact. Alright, now that we've made clear to ourselves what we want to implement, let's go ahead and create this state machine in VHDL. To get us started, I'll head over to the test bench from the previous tutorial and copy everything to the new file, which I will save as T20 for tutorial number 20 underscore finite-state machine tb.vhd. Remember to change the entity name here and in the architecture as well. We're not going to use any of these integer type signals, so I'll go ahead and delete them. We'll keep the clock and reset signals. I'll also delete the instantiation of the timer module from the previous tutorial. The test bench sequence doesn't do much other than taking the device under test out of reset, and we need that, so I'll keep it. In the previous tutorial, we lowered the clock frequency to 10 Hz to speed up simulation time. I'm going to increase it to 100 Hz for now. Not that it makes any difference, but then it will look more like the clock changes really fast in the waveform window, which is of course the case in the real world, where clock speeds are in the megahertz range. Okay, so let's head over to the timer module from the previous tutorial and copy all of the code to a new file, which I will name T20 underscore trafficlights.vhd. Remember to change the entity names both places in the file. As I already mentioned, we're keeping the clock and reset signals, but these integer signals in the entity, we have to delete them. We don't need this signal and procedure from the previous tutorial, so I'll delete them as well. Finally, in the process down here, I'll delete the variable declaration, the reset of the signals that we already removed, and the calls to the procedure which we've already deleted. This will be our starting point for this tutorial. We're now left with an empty skeleton of a standard clocked process, triggered by the rising edge of the clock. In here, if the if negative reset equals 0, we'll assign our reset values. The else branch will be reached when the module is not in reset. This is where we want to put most of our code. Okay, so we're going to implement a finite state machine, and the first thing I always do when creating a state machine is to declare the state signal. We do that by first declaring an enumerated type with all the different states that we need. I'll start by typing the keyword type followed by the name. The name could be anything, but I'll name it t_state. After the name, I'll type the keyword is, and then inside of parentheses, we're going to list all of our state names. North next, start north, north, stop north, west next, start west, west, stop west. And finally, we'll close the parentheses and terminate the line with a semicolon. What we've done now is to declare a new type, which can have any one of those 8 values. Then on the next line, I'll create a new signal, which I'll give the name state. We'll set the type of this signal to the one that we just created, t_state. Now this signal can have any one of the values that we declared in the line above. This is a standard enumerated type declaration and state signal declaration. The next thing we need to do is to give the state signal a reset value. I think we should use the north next state, in which the lights are red in all 4 directions. That seems like a safe state to go to when the module is reset. Okay, so now that we know which state is the first one, we're gonna implement the rest of the state machine down here in the else branch, where the module is not in reset. We're gonna do that by using a case statement on the state signal. What we learned about case statements back in tutorial number 14 was that they can be used to make the program take different branches based on the value of a signal. The value of the state signal determines which state the state machine currently is in, and we want the program to choose a different branch for each one of the states. I'll create the first one by typing when north next, arrow notation. Then I'll do the same thing for all of the other 7 states. And finally, we'll close the case statement with an end case tag. Okay, so initially the state signal will have the north next value. At the first rising edge of the clock after the module comes out of reset, the program will enter this branch. When that happens, we eventually want the state machine to go to the next state. We'll do that by assigning to the state signal the value start north. Then on the next rising edge of the clock, the program will enter this branch. Now we want to proceed to the next state, which is north. From the north state we want to go to the stop north state, and from there to the west next state. From west next we go to start west, from start west to west, and from west to stop west. Now we are at stop west, which is the final state. What do you think we should assign to the state signal from here? That's right, we go back to the first state, which is north next. And that's the infinite loop of finite states which this state machine will be working its way through. Let's stop there and head over to the test bench and instantiate this module so we can try it out in the simulator. I'll name this instant I_traffic lights. After the colon entity work, we've got to specify the name of the module, which is T20_traffic lights. Inside of the parentheses, we'll write the name of the architecture, which is RTL. On the next line, we'll enter the generic map. The only generic in our module is the clock frequency hertz signal. We already have a constant for this in our test bench, so we'll assign this value. Next up is the port map. Currently the clock and reset are the only 2 inputs. We'll connect them to those signals which we've already declared in our test bench. Now we're ready to simulate this design and see what the state signal looks like in the waveform. I'll save the test bench and head over to the traffic lights module and save it as well. I'm adding the 2 VHDL files to our ModelSim project, then I'll compile them, starting with the traffic lights module before the test bench. I'm starting the simulation and selecting the I_traffic lights instance in the hierarchy view. That will cause the signals from that module to become visible in the objects window. I'm selecting the clock, the state and the reset signal, which I will add to a new waveform. Now I want to run for 1 second of simulation time, so I'll type in the console window run 1 sec. When we zoom out, we can see that the state signal has changed a number of times. Let's zoom in on the start to see what's going on. Initially, while the reset is still active, the state signal has the value north next. It has this value because that's the leftmost state in our type declaration. That's the reason why it has that value right from the start. By default, an unassigned signal gets the leftmost value from the type declaration. But we also use the north next state as a reset value. So as long as the reset signal is active 0, the state signal will have this value. At the third rising edge of the clock, the test bench releases the reset by setting the negative reset signal to 1. After that, the state signal changes at every rising edge of the clock. Let's zoom in a bit further so we can see the state names more clearly. The first state it transitions to after reset is the start north state. Then follows north, stop north, west next, start west, west, stop west, and finally we're back to north next. From there, the pattern will repeat itself. But you know, right now, the module isn't doing anything useful. The state signal is changing, but that's just an internal signal in the module. It isn't visible from the outside at all. Imagine if we wanted to use this module to control the traffic lights in an actual intersection. We'd have to add some outputs to control the red, yellow and green lights in different directions. So let's add some standard logic outputs to the module's entity. The first I'll name north red. We'll hook this up to the red light in the north-south direction, so that when the value of the signal is logic 1, the red light will be on, and when it's logic 0, it will be off. Similarly, we'll create a north yellow and north green output for controlling the yellow and green lights. We'll also need a similar set of outputs for controlling the lights in the west-east direction. I'll name them west red, west yellow and west green. We don't need to declare any signals for the southeast directions. The lights in the north direction are always the same as the one in the south direction, and the lights in the west direction are always the same as the eastbound lights. First of all, I'll just copy the whole column of signal names like this. You can do this in Notepad++ by holding down Ctrl and Shift while using the arrow keys, because the first thing we're going to do is to add a reset value to them. I'll make some space and paste them in like this, then I'll assign to them 0. But actually, I don't think 0 is the best value for all of these signals. Imagine if the traffic lights were operating and suddenly, for some reason, the module resets from the outside. Then this code will result in no lights on at all. I think it would be safer to light up the red lights in the event of reset. To do this, I'll assign to the north red the value 1 and to the west red the value 1 as well. Okay, so now that we've got the safe reset values in place, we're going to take control of the traffic lights down in our state machine as well. Starting with the north next state. How about if I simply paste all of the signal names in here and assign a value to each and every one of them? If we check the state machine diagram, we see that in this state the lights should be red in all directions. So I'll assign 1 to the north red and west red and 0 to all the others. Now we could continue to follow this recipe for all the other states, assigning to each and every signal in all the states. But then you would be working too hard, because there's an easier way to do this. Instead, we'll use the method of default signal values. Right here, before the case statement, at the start of the process, I'll assign the default values to all the outputs. I'll simply assign 0 to all the outputs at once at the start of the process. So now we are assigning one value to the signal in the north next branch and another one before the case statement. Now how can this work? We've already been through this back in tutorial number 6, which was about differences between signals and variables, but I'll give you a quick recap. At the rising edge of the clock, this process will wake up. At the first line, we're assigning 0 to the north red state. But then in the north next branch, we're assigning the opposite value of 1. So what happens? Will the signal first get the value 0 and then the value 1? No. The code within this process is run in 0 time, and assigned signal values are only updated when the process goes back to sleep, after the code reaches the end of the process. So the signal will only get the last value which was assigned to it. This means that we can delete all 0 assignments from the case statement, as they will be covered by the default values. Less clutter, and all of the outputs are guaranteed to be set to 0 if you forget an assignment in one of the states. Alright, let's go over to the start north state. In this state, the lights are red and yellow in the north-south direction and red in the west-east direction. To implement this behavior, we'll assign 1 to north red, north yellow and west red. Next up is the north state. In this state, the lights are green in the north-south direction and still red in the west-east direction. We'll light up north green and west red. In the stop north state, the light is yellow in the north-south direction and red in the west-east direction. Assigning 1 to the north yellow signal and 1 to the west red signal should do the trick. In the west next state, the lights are red in all directions. This is the same behavior as in the north next state, so we'll simply copy a couple of lines from there. In the start west state, the lights are red and yellow in the west-east direction and red in the north-south direction. So we'll assign 1 to north red, west red and west yellow. Then in the west state, the light is green in the west-east direction and red in the north-south direction. We'll assign 1 to north red and west green. And now we're at the final state, which is the stop west state. Here the light is yellow in the west-east direction and red in the north-south direction. We'll power up the north red signal and the west yellow signal. We're done with this module for now, so I'll go ahead and save this file. But we still have some work to do in the test bench. We've created a bunch of new output signals which we haven't connected to anything in the test bench yet. I'll just copy paste them into the test bench, but here the syntax is a little bit different, so I'll add the keyword signal in front of them. And then the direction keyword out makes no sense in the signal declaration, so I'll delete that. Now that we've declared the new signals in the test bench, we're going to have to connect them to the device under test, which is the traffic lights module. I'm going to use Notepad++ column edit mode again to copy all of the names at once and paste them into the port map of the module instantiation. Paste once more, then add the assignment operator in between the port name and the local signal name. And finally, comma separate the lines, and we are done with the changes in the test bench. After I've beautified the code a bit, I'll save the test bench and head back to the traffic lights module. Now we are going to have a look at the waveform and see how the state machine controls the new outputs. Compile, restart the simulation, and add the new signals to waveform. To make the waveform a bit more readable, I'm going to right click and add a couple of new dividers so that the signals are grouped into north, south and west, east. Now we're all set, and I'm going to type run 1 sec in the console, which should give me 1 second of simulation time. When we zoom out, we can see that there's stuff going on with our new output signals. Let's zoom in a bit more so that we can relate the output signals to the current state of the state machine. At first, while we are in the north next state, the north red output is 1 and the west red output is 1. That sounds about right. But then in the next state, which is the start north state, the signals are unchanged. Let's check our code to see if we did something wrong. In the start north state, the north yellow output should have been activated, but in the waveform it's still 0. In the next state it changes to 1, but this is the north state, and here the north yellow signal should have been 0 and the north green signal should have been 1, but it isn't. It seems that the output is always delayed by 1 clock cycle, causing stuff to happen in the wrong state. The reason for this is of course that the output signals and the state signal change simultaneously. For example, in the north next state, these outputs are set to 1 and at the same time the state signal is changed to start north. So they all change at the exact same time step. Another more serious problem which we have been ignoring is the speed that things happen in. If I zoom out, we can see that the state machine has gone through all of the states a lot of times. And I simulated only for 1 second, so this is way too fast. If we can delay the state changes sufficiently in time, the module would work as intended. If you've been following this tutorial series, you already know how to do that. We created a timer module back in tutorial number 18. Let's use some of the things we learned to control the timing of the state machine. I'll head over to the declarative region of the architecture. Here we're going to declare a new signal with the name counter of type integer. We're going to use this signal for counting clock periods. I could leave it like this, but this time I'm not going to. It's good practice to define the range of the integer signals. This is a way to tell the compiler how many bits it needs to reserve for implementing this signal in hardware. After the range keyword we type 0, 2, meaning that the lowest value this signal can represent is 0. Then after the 2 keyword we have to specify its highest value. I'm gonna base this value on the clock frequency, which we already have access to through the generic port. So I'll paste that in there. The clock frequency tells me how many clock periods there are in a second, and I want to count up to 1 minute 60 seconds. So there's our counter signal, capable of counting up to 1 minute worth of clock periods. What's the next thing you've got to do after you've declared a new signal? That's right, we got to give it a reset value. I'll give it the value of 0 because we want the timer to start counting from 0. The counter signal is for counting clock periods. One way to implement this is to add a counter gets the value of counter plus 1 line outside of the case statement. This line will run every clock cycle and the counter will increment as well. Now we've got a reliable way of measuring real time. We can use this counter signal for controlling how long the state machine stays in each state. To prevent the state from changing, we need to delay the assignment of the new state to the state signal. We can do that by enclosing it in an if statement. I'm typing if counter equals clock frequency times 5 minus 1, then. This statement is true only when the counter signal has counted 5 seconds worth of clock periods. We need a minus 1 because we're counting from 0. If we didn't have minus 1, we would actually be counting one too many clock periods and the timer would last a little bit too long. Okay, so the new state assignment will be delayed for 5 seconds, but we need to add something more in here. We need to reset the counter signal, otherwise it would just continue counting up and beyond 5 seconds. So we'll add a counter get the value of 0 line here. Next up is the start north state. In this state the light is red and yellow in the north-south direction. I want this and all the other intermediate states to last for 5 seconds. That's typically how they appear to me when I'm driving. So I'll just copy the if statements which last for 5 seconds and paste it here. In the north state, the light is green in the north and south direction. Obviously, this state needs to last longer than 5 seconds. I think a minute sounds about right. I'm typing if counter equals clock frequency. Actually, I think I got the name of this constant wrong. It's not clock frequency, it's clock frequency hertz. I'll just change that really quickly. Where was I? Right. If the counter equals clock frequency hertz times 60 minus 1, then. And of course we have to reset the counter in here too. So this expression is true if 1 minute has passed. This will ensure that the light stays green for exactly 1 minute. The next state is stop north. This is a transitional state, so we'll copy the code that will delay the state change for 5 seconds. The same is true for the west next state and the start west state, so I'll do the same there really quickly. Then we are at the west state, which gives the green light to the west-east direction. We want this state to last for 1 minute, so I'll copy the code that does that. And finally, the last state is stop west, which is a transitional state. We want the yellow light to last for no longer than 5 seconds. After 5 seconds, the north next value will be assigned to the state signal, which will cause the whole sequence to repeat itself. Ladies and gentlemen, it's time to simulate the final design for this tutorial. If you've been with me this far, you must be eager to see the end result. Save, compile, restart the simulation, add the counter signal to the waveform. I want to run this simulation for 5 minutes, so I'll type in the console run 5 min. When we zoom out, we can see that a different pattern is emerging than before. The counter signal is counting all of the time, which is good. If we zoom in on the start of the sequence, we can see that the first state is north next. After that, start north. And then comes the north state, which seems to last for a really long time. It should be a minute though. If we zoom out again and focus on the north state, we can see that there are only 2 signals that are active in this state, north green and west red, which seems about right. While in the west state, north red and west green is active, which is also correct. In the second half of the timeline, we can see that the north state is active again, and the pattern repeats itself. The time value, which is displayed in the timeline, is shown in nanoseconds. Normally, nanoseconds is fine for working with digital logic, but sometimes you want to change the time unit to something else. In ModelSim, you do that by right-clicking on the timeline in the waveform window and selecting Grid, Timeline and Cursor Control. Then you can select something else from the time units drop-down menu. Let's change it to seconds. Let's add another cursor to the waveform window. We can use the 2 cursors for measuring time. I'll place one exactly on the transition to the north state here, and the other one on the next transition. Then we can see the difference in simulation time in between the 2, which is 60 seconds. Sounds about right, doesn't it? There you have it, your very own traffic lights controller module. The ability to create finite state machines like this is one of the most important features of the VHDL language. If you pursue a career as a VHDL developer, you will be creating state machines like this all of the time. Whenever you need to implement some sort of protocol or algorithm in VHDL, state machines are the right tool for getting the job done. The challenge is really just to define the states and the transition between them. Once you've come up with a state diagram that actually describes what you're going to implement, converting it to VHDL code is pretty straightforward. That's all I had for you in this video about finite state machines in VHDL. Thank you for watching. If you enjoyed it, you can find more tutorials and blog posts at VHDLwhiz.com.